all up. So to start, Hess's law. So in Hess's law, I don't have like a formal definition of Hess's law here, but basically what Hess's law is saying is, in chemistry, there are often multiple steps in a reaction. So up to now, we've only ever showed you one step, which would be the observed reaction, or sometimes I call that the global reaction, the main reaction. In chemistry, there's almost always what we call a mechanism. So in other words, chemistry occurs in steps. Okay? So for this simple reaction between nitrogen and oxygen to make two NO2 to make two nitrogen dioxides, it actually starts with step one, where one single nitrogen reacts with one single oxygen and makes two nitrogen monoxides. And we note that that's an endothermic step, that first step being positive 180 kilojoules. So now in the second step, check this out. The product from this first reaction now becomes a reactant in the second step. And it reacts with another oxygen to make two more nitrogen dioxides. And this is an exothermic step. Okay? And so what's important to note, when I add step one and step two, check out what happens. So the two NOs cancel with the two NOs, right? So later on in Chem 110, we'll start to call this an intermediate. So we're not going to talk about intermediates too much in this class, but it is a chemical intermediate. It appears in one step and disappears in another step. Okay. We also note that, look, there's two oxygens that get added up to give me my two oxygens right there. All right. And everything else follows down the line as we're adding these reactions together. And what we get is the main reaction. Okay. And also what's important to note, in this is Hess's law here, when I add these two steps together, I also add the enthalpies together, okay? So positive 180 plus negative 112 gives me 68 kilojoules. So overall, globally, this reaction is endothermic, okay? So graphically, we can see that right here on this chart. So here I have my initial state of nitrogen and two oxygens, okay? There's this large endothermic enthalpy, 180 kilojoules, that's required for the first step. We often refer to that as an activation energy when a reaction has a large and positive first step. That's the energy that's required to activate the reaction, to get it going. Okay, and then so now we have the products of the first reaction, so the intermediates, right? And then those go on to react and release some energy. And so now my final state is right here. Okay, and so we have to remember, because enthalpy is a state function, only the initial and final state matter, which is shown right here, right? The initial to final. It's as if this mechanism is not even present. And that's why up to now, we haven't really been dealing or seeing with these mechanisms or steps, because they often can happen really fast. It can often be very difficult to get our hands on those intermediates and see what's going on. So we're usually only sensitive to the initial and final state in a chemical reaction, which is why we deal with this delta H as a state function. Okay. So now this is a bit of an esoteric exercise, but all the same, it's a good exercise for applying Hess's law. Okay. So suppose we want to calculate the delta H for this reaction right here below. Okay. But we don't know what any of its steps are. But we are given these, what I'm going to call elementary steps right here. So maybe we're able to look those up in a book somewhere. And we notice that they're not quite in the order or in the stoichiometric proportions that we need. So in this exercise, I'm going to show you how we can flip things and rearrange them to add these two steps together to give us this global or observed reaction. Okay? So this is kind of like solving a puzzle, and everyone's going to do it a little differently. So I'll just walk you through how I do it. So the first thing I notice is that ammonia is a product right here in this reaction. However, it is a reactant in this reaction. So the first thing that I want to do is take this step number 1 and flip it. Okay? So I'm going to write it as the following. I'm going to write it as 3 halves H2. I'm going to skip writing the phases for now just to make life a little bit easier. And so I'm just writing this above reaction in reverse. Okay? And when I do that, it changes the sign of delta H. So up here it was positive 46 kilojoules, but when I flip it, it becomes negative 46 kilojoules. Okay? So now the next thing I recognize is that I also have this reaction here where H2O is a product, but down here I need it to be a reactant. So I'm also going to flip this reaction. Okay, so I'm going to write that as 2H2O goes to 2H2 gas plus O2 gas. And of course, because I flipped it, I also changed the sign again. So positive 484 kilojoules. Okay, so now this is the first step that I like to do. I like to get everything kind of arranged in the right order. But now what I'm going to have to do is multiply these reactants just like we did with balancing redox reactions to get the right number of reactants. Okay. So the first thing I notice is I need 4 of these ammonias, and actually what I'm realizing is I think that, let's see, oh, I'm looking at my cheater notes, and I think that I have a typo in this problem. Okay, let me check really quick. Oh my God, yes, I have a typo in this problem. Okay, so there should be a 2 right there. Okay, there should be a 2 right there. I'm looking at my cheater notes right here. Whoops. Okay, so what that means now, what I want to do to get 4 ammonias, I'm going to multiply this whole thing by 4. Okay, times 4. And so not only is that going to give me the right nitrogen and ammonia, right? 4 times 1/2 gives me 2 nitrogens and 4 ammonias. But I also need to remember that I'm going to multiply this by 4 as well. Okay? And so now, let's see. So when I kind of scan through, right, I can see 4 times 1/2 nitrogen is going to give me 2 nitrogen, which I need. And 4 times NH3 gives me the 4 ammonia. So I also need that as well. Okay. And so that's also going to give me a whole bunch of hydrogens, which hopefully I can cancel. All right. And so now I'm going to need to do the same on this reaction. And what I'm going to do, I'm going to scan through and see, so for example, I've got 3 oxygens right here, but I've got none. So I'm just going to say times 3. And yes, that's going to be perfect because, right, I need 6 waters, and then the 3 times 2 is going to give me my 6 waters. And we'll see what happens to the hydrogen. Hopefully that cancels out this intermediate hydrogen, okay? And then I also remember that I'm going to have to multiply this energy by 3, okay? So let's keep that going. And then now I'm going to add them all up, okay? So I've got 4 times 3/2 hydrogen. That's going to give me 6 H2s plus 2 N2s. And now 3 times 2 gives me 6 H2Os. And then look, now I've got 6 H2s plus 3 O2 plus 4 NH3. And I can see my hydrogens cancel. Okay, so great. So now I've got 2 nitrogen plus 6 oxygen plus 3, plus 6 H2O plus 3 oxygen plus 4 ammonia. So that gives me the correct answer. And then now down here for my delta H, it's going to be 4 times negative 46 kilojoules plus 3 times 484 kilojoules. So let's see, that's going to give me 46 negative times 4 plus 3 times 484 equals, and let's see here, what do I get? Yes, wonderful, that's the right answer. So I get positive, let's see, because this is addition, it's going to go to the nearest whole joule. So that's 12, 1268, 1028, 1268 kilojoules. So endothermic, okay? So now I've got another problem here that I'm not going to work out in the interest of time, but you should definitely try and work out this problem for yourself. I am going to put the solution to this in the notes. So I'll work this one out and include it in the notes, okay? So I want to try to keep these videos shorter, so that's why I'm going to skip doing this. So this will be good practice for yourself.